Welcome to Study Loop.
Okay, let's get started. So, so far, have you have learned how to solve the second order linear differential equation. However, in this case, you have non-linear differential equation because of this sine term. So, what is your first step? You have to linearize this differential equation, right? So if you look at the hint says for small values of theta, we can use the linear approximation. And so this sine theta is almost the same with this theta. So we can transform this differential equation, right? Now, now let's move on. Look at the A. Find the equation of motion of a pendulum with length 1 meter, which means this L is 1. And then theta is initially 0.2 radian. That means theta of 0 is 0.2. And then initial angular velocity is 1, right? So we have this second order linear differential equation, right? So if you have a linear differential equation, what is your first step? Your first step is solve the characteristic polynomial. So this represents the characteristic polynomial, right? So in this case, it's a second order, so d squared plus g. Here g is a constant, g is the gravitational acceleration, right? So if you solve this characteristic polynomial, you get two complex solutions, right? So if you have a complex solutions, then what is your solution? What is your real solution? What is the solution of the solution to the differential equation? The solution has the form of this one, right? It is a linear linear combination of sine and cosine, right? And here a and b are just constant. So what is your next step? We have to find these a and b. How? By using these two initial conditions, right? So when t equals to 0, the initial angle was 0.2 radian, and the initial angular velocity was 1, right? So by using these two conditions, we can find the two constants a and b. So if we plug 0 to t, then it becomes 0. So your p is 0.2. And then if you differentiate it and then plug 0, then this term will vanish. So you get square root of g times a equals 1, which means a equals 1 over square root of g. Yep, right? So this is your final answer to a. But here it is 2.2, right? So let's move on. B, what is the maximum angle from the vertical? So we have to find maximum of this function, right? And then there can be two ways. First, use the extreme value theorem. So by finding the solution of this equation, right? Do you remember this one? Yep. By finding the solution of this equation, you can find the local extrema, right? And then by using the second derivative test, you can determine whether there is a local maximum or local minimum. And then you can find the maximum easily, right? And then the second way is use formula. I'm not doing the first way because it is not easy to compute these, these constants. So I'm going to use the formula. Then what is the formula? So when you have a function of this form, then you can easily find the maximum. It is square root of 13. How did I do that? It is square of this number plus this number, and then take a square root, right? So in general, if you have a constant a and b, then your maximum will be square root of a squared plus b squared, right? Yeah. And then by using that formula, we can compute the maximum very easily. So square root of 1 over g, because I squared it, plus 0.2 squared. So it is 0.04, right? It is approximately, by using calculator, you can compute this. So far so good, right? It's not that hard. And then let's move on. See, what is the period of the pendulum? So that is the time to complete one back and forth swing. Again, we can use the formula. In this function, we can easily find the period. It is 2 pi over 3. How can I find this? So in general, if you have omega times x in the trigonometric functions, right, then your period will be 2 pi divided by the absolute value omega. So in this case, our omega is square root of g. So we have this period, right? Yeah. Nothing difficult. So let's move on. So D, when will the pendulum first be vertical? So if you look at this picture, this line is vertical. So the problem asks you to find the time when this object pass through this point. So we are going to find the time. And at this point, the angle becomes 0. So we have to find the time which satisfies this equation. Theta of t equals to 0, right? Then we can set this equation, right? I just used the formula for theta of t, right? And then since I want to push the t, collect the t in one term, I divide it by cosine of square root of g times t to collect t in one term. Then we get this, the second equation, right? Here, what is this? Sine over cosine. This is tangent of square root of g times t, right? Right? Then we get this equation. And then here, we have to think, at this time, at this t should be positive. But if you find the solution of this one, or this one, look at this y equals tangent x graph. If you remember, by using arctangent, you can find the point, this point, right? Well, for example, this is your negative 0.2 times square root of g. Then you can easily find this point. However, this point is negative, and we need a positive number. So we have to find this point. So the difference between these 2 points is exactly pi. So by adding pi, we can get the exact solution. So here, this one becomes this. So square root of g times t equals arctangent of negative 0.2 times square root of g plus pi. And by using calculator, we can compute this approximately. Then you get 2.58. Am I right? 58. Yep, this is right. This is an approximated solution. Yeah. So approximately after 2.58 times later, the pendulum will first be vertical, right? Now let's move on. E. What is the angular velocity when the pendulum is vertical? So at this point, we have to find the velocity, the angular velocity, right? So to find the angular velocity, we have to differentiate zeta and then plug the exact time. Yep. So to plug this number, then here square root of g times square, I mean the rectangle, I mean the t, we already found this one. So 2.58. So by plugging this number, we can compute it easily. Then by using calculator, this one is negative 0.83. I mean 84, right? So we can find the angular velocity. Here, notice that it is the absolute value of this one is smaller than 1, which is the initial angular velocity. Why is this happening? Well, because this is an approximated solution. I mean, when you if you remember the physics classes, the potential energy plus physics the kinetic energy should be equal. So when your pendulum will be the lowest, it should be fastest. But since we used the approximating model, not exact model, we have this result. Well, so thank you.